Alors, bonjour tout le monde et bienvenue à ce colloque des sciences mathématiques du Québec organisé conjointement par le CRM et l'ISM. Donc, il me fait plaisir d'accueillir aujourd'hui Ashkan Ertefaie, qui est professeur agrégé au département de biostatistique, épidémiologie et informatique de l'Université de la Pennsylvanie. Ashkan a fait son doctorat à McGill avec Massoud Asgharian et David Stevens. Il a complété en 2011. Il a ensuite travaillé à l'Université du Michigan comme stagiaire postdoctoral et aussi à l'Université de Pennsylvanie. Il était jusqu'à tout récemment à l'Université de Rochester comme professeur agrégé. Ashkan travaille donc en inférence causale, médecine personnalisée, modèles semi-paramétriques, données de survie et sur les traitements START. Et il va nous parler aujourd'hui d'inférence causale pour événements récurrents avec un événement terminal. Juste avant de lui laisser la parole, donc la semaine prochaine, n'oubliez pas, on a Nilima Nigam de Simon Fraser pour la journée des femmes en mathématiques. Donc, ce sera au CRM à 15h30. Ashkan, thanks a lot for...
Sure. Thank you. Thank you for a nice introduction. Let me see if I don't see, yeah. So this is what I forgot to add. I forgot to add my collaborators here. On this project, I work with my former postdoc, Ben Baer, Robert Strotherman, and my current postdoc, Trang. They're all working on this, collaborating on this project. So I'm going to talk about recurrent event processes a bit, not very in depth, but the main challenge is that for drawing causality, this terminal event can be quite challenging for the reasons that we will see. So just a quick background or intro on why we care about recurrent event processes. In many, when you're dealing with chronic diseases or even long-term exposure to certain exposure like air pollution, for example, then the adverse events of that exposure, or in general, the recurrent events, it doesn't have to be adverse necessarily, it happens over time. So it's not just, we typically, in most of the clinical research, they are interested in the first event, like the first cardiovascular disease after being exposed to certain level of air pollution. But we know that it's not, the first one is important, but then the later on, how much you get of these events is also critical as it reflects the burden of that exposure. But it gets a slightly more complicated even in non-causal setting, but there are tons of work on that. So we are interested, my focus is on causal inference. There's a huge interest in causal inference in the context of survival analysis. And this one is just tries to extend it to recurrent events. There's, as I said, there is a huge literature on recurrent event analysis. It's not a new topic at all. And as you see, I don't know if I probably missed some, but I have it from 97 and the book by Richard and Jerry Lawless, 2007. And I think there's an earlier version of that, right? It's a 95, it's a book 95? It's the second edition, 2007, anyway. So, but the focus on causality of this recurrent event processes has been very, very limited. I would say Doug Schaubel and Zhang, I would say, to my knowledge, is the first one that started looking at the expected number of recurrent events under certain exposure. And it's a time point, it's a single time point exposure, it's not a longitudinal study. And they have censoring events, and they use double inverse probability weighted to adjust for censoring and propensity score. I refer to Schaubel and Zhang later on. I'll present the estimator. Yanvin, 2023, they did another inverse probability weighted estimators, but they looked at the event, the terminal event like death, as a mediator. So they look at it as in the context of mediation analysis and like a direct effect. So they intervene on a death. What would have happened had death had not been happened? How many events I would have observed on this individual? So death is an event that that mediate the effect of exposure on the recurrent events because it terminates the events. You cannot have events in this setting after failure. Jensen and Sue, I believe Sue's, I don't know, I guess maybe he or she was a PhD student at McGill, so has worked with Robert Platt and Russell Steele. So this is, Ross has done this work, and I think it's a 2022 one. They do causal inference for recurrent event as well, but they don't consider termination due to failure, like a terminal event like death. They do have multiple robustness, but they don't have efficiency. Sorry, yeah. So what would be the contribution of this talk? Well, let me clarify. So some of this, I think one of those bullet points I don't present it because of time, but there are, in the archive paper, we have a more extensive discussion of all of this. So we characterize coarsening at random for causal recurrent event analysis. So coarsening at random characterizations require some work, and I'll show you what is being assumed usually, even in typical survival analysis, is stronger than coarsening at random that is required for identifiability. And so we identified a nuisance parameter and estimand, as I said, under the weaker condition and full independent censoring. Class of influence functions, I don't have it here, but we use that class of influence function to then we get to the nonparametric efficient influence function for a number of recurrent events. And we show that how we can, what assumptions we need to make sure that the estimated asymptotic linear, meaning that the remainder terms will vanish at the root n rate that is desired. One small point here is I also don't require absolute continuity. It's a subtle point, I'll talk about it, meaning that censoring and failure can jump at the same time. And it can make some challenges, I'll talk about that. So pretty standard notation, particularly for survival. L, let's say, is my baseline. A is my binary treatment. T is T0, T1 with the star or asterisk. They are potential failure times under A equal to 0, A equal to 1. N0, N1, they are right continuous potential recurrent event processes, is the same kind of definition of counting processes, but it's just the potential at the world being assigned treatment 0 or 1. C0, C1, censoring variables, pi propensity score. H is the survival function for failure time. K is the survival function for censoring. I will remind you when I'm using H and K. The last one is also, as I said, we are assuming that recurrent events stops when the failure occurs. Right? In the context that death, it's sensible. It means when you die, you cannot have event. So the full data, the full data, meaning that the data, hypothetical data that you wish you could observe to have your life simple, would have been the data without any coarsening. So you would have L, T1, T0, N0, N1, like all the potential outcomes, everything. But of course, we don't observe that. The observed data is, again, the typical, the coarsen one is L, A, the treatment assignment. So it's a level 1 coarsening. We assume that the treatment assignment happens before the censoring. So first treatment assignment happens, and then this is the indicator of whether we observe the failure or censoring delta. X is a minimum of a TNC, and NT is the number of events that we observe up to time T. That can potentially be interrupted by C. Failure process, again, is the classical definition. It's just a indicator. So it needs to only jump once because the failure censoring happens just once. So this is the indicator of X, the event, either censoring or failure, for delta equal to 1. So this means basically the failure, if the failure happened before T, if the censoring happened before T, then these processes jump. What we are interested in is the expected number of NA star T, expected number of potential recurrent events up to time T under treatment A. Let's call it mu. Fundamental issue with this, when it comes to causality, causal inference, precision medicine, is that this guy can be small or large depending on the survival. So when this number, as I said here, so the failure is likely to occur early. So if you don't have that many, if this number, the mu, is small, it's either the recurrent event is not happening that much, or the individual just dies. And these are very two opposite direction of what you are expecting. You don't want to kill a patient and not have cardiovascular disease, for example, right? So this becomes really, really challenging. So interpretation of this guy, of this mu guy, is challenging. How do you interpret this? All by itself, it doesn't have interpretation because you don't know you wanted the small or you wanted large, right? And being small is not necessarily good. So it's tied very closely to the notion of eta, which is the survival function, the typical survival function. Is the probability of T greater than T, capital T greater than T. So I leave it at this mu for a counting process, recurrent event process, and eta is the failure process, basically, related to that. So I'm assuming that I have a discrete landmark times, that these things are being measured, that the jump can happen. And the full data in this discrete landmark time, my full data are all those mu's and all those etas, right? So the number of recurrent events at time t0, the number at time t1, survival t0, survival probability t0, survival probability t1, and so on and so forth. So it's a like I would say it's a 2m dimensional, or sorry, 4m dimensional vector of estimates. So by the way, if you have any questions, please ask. Yeah. Potential. It just means potential. Yes. So this is, right, that's a good point. So this means that E star, it means the data distribution under P star, on the potential world, right? So expected value given on the universe that you observe the potential, that's a P star. And that's a P star for that world, right? And so of course, we're gonna need identifiability result to link the E star to E, expected value in the observed world, P, under the P data distribution. So a coarsening at random assumption, we do not observe, all we observed is O, is the data, observed data. What we want, our estimate comes from potential outcomes. So we need some kind of assumptions to link these two. And if you want to do careful derivation, we went through this. So typically what is done is you write your identifiability condition and you see what conditions you need to get to the identified potential outcome of your estimand of interest. But those do not necessarily give you the minimum assumptions you need. These are minimum assumptions you would need. So like I just want to point it to one of these that is oversighted oftentimes in the literature is this guy. So this, even in the survival setting, right? In the survival setting that you have all the jump process for a failure, you need the independence between T's and A's only when the C star is C is less than T. In other words, when this independence assumption for C's that are greater than T can completely break this independence assumption. So what I'm saying is, this is what you see here is the minimal assumption, is the true coarsening at random assumption to identify the causal parameter of interest. I'm going to dive deeper into this. So this is typically the assumptions you see. You just see this is called independence censoring assumption, conditional independence censoring assumption, right? The argument is that the assumption is being made typically in the literature is stronger than what I said. So the second and third conditions that I just showed you, these two, they are implied by this guy because this is a stronger condition. So the second condition restricts the independence to the region where censoring occurs before failure. If censoring happens after failure, it can be completely depending on T. I don't care, right? And also, the third condition asserts that observing a failure is independent of recurrent event history and counterfactual under the alternate treatment. So this one. Right? So you want this guy to be independent of this conditioning on TA. So conditioning on TA, meaning that you're basically treating this guy as a fix. So it's an indicator of CA being greater than some T, and you want this to be independent of your survival in the other arm, in the opposite arm. One reason that although people most of the time use this condition and still get the same efficient influence function is because your data cannot differentiate between this and the one I have here. So what I'm trying to say is the coarse setting, the minimum coarse setting and random assumption that I'm showing you here is just a mathematical practice, but it doesn't change your influence function because your data cannot differentiate between the two, a stronger and weaker condition. But all the identifiability results I show you, as I said, will rely on these three weaker assumption compared to this one that is typically done. Okay, so some extra notation here. I defined the at-risk process YU, being that showing that it's an indicator function whether an individual is at risk or not, as being X, the censoring minimum of censoring and failure being greater than equal to U. And this is a very typical at-risk process in survival analysis. And H, remember that was the survival for failure. It's just one minus the hazard. It's the product integral. And I define where the hazard function defined this way. Again, this is the typical way. It's just nothing special there. I believe Gill and Johansson talked about this in '97 in detail. And this would be, the K would be the one that is slightly more subtle, is the censoring one. As you see here, the censoring intensity is similar, it's analog to this one. You just replace NT by NC, which is the counting, the event process for the censoring. But you need to replace Y with Y dagger. And this Y dagger has this definition. It's slightly different, but the difference is important. So here is the typical at-risk process for the failure, and this is the at-risk process for the censoring intensity. So what it says, so for censored individual is exactly X being greater than equal to U. But for individuals that are failed, X has to be strictly greater than U, cannot be equal to U. That's because if X is equal to U, it goes to here. Let me go back to the delta definition. The way I define delta, it says T is less than or equal to C, meaning that T, if both of them jump at the same time, I count it as a failure. So I give priority to failure, right? And these things don't happen when you have absolute continuity in the distribution, that they cannot jump at the same time. This just happens when you want to relax absolute continuity and you observe things on landmark times, which is the setting I'm dealing with. So this becomes, you cannot have X greater than equal to U, because when X is greater than equal to U, means that failure happened at time U, and C, which is the censoring, has to be greater than U. So the time for being censored is past. So that's why it has to be greater than U, strictly greater than U, so that the person or the sample is at risk for censoring at the time of U. So this small change causes lots of trouble if you want to do normal, like martingale theory on this. So I think I talked about all of this here. I talk about it a bit more here. So now I define my MC process as just NC minus the integral of the at-risk process times the D of intensity, which is kind of resembles the way the martingales are defined. But I don't call it martingale yet. So I just call it a process. This is an MC process, right? It's very, very similar. It's martingale is like a residual, and residual is what it appears in the influence functions as a nuisance. It generates the nuisance tangent space. So this guy is going to play an important role in my efficiency theory. The difference is that between Y and Y dagger is, although the usual at-risk process Y is left continuous, this Y dagger is neither left continuous nor right continuous. That's right away creates a huge problem because it means this guy. It means YT, we know YT is predictable with respect to an appropriate filtration, whatever filtration like FT minus. But the Y dagger is not predictable. So that makes the martingale theory, the entire martingale theory here, pretty challenging, right? It's showed Ben, my postdoc, and Rob in 2024, they show that it is actually a martingale. It's a quite heavy theoretical work, but they show that it satisfies all the martingale theory. The other thing is for stochastic integrals, we usually like this guy, the integrand, to be left continuous, because otherwise the stochastic integral is not well defined. So it's just from a mathematical point of view, that's one thing that contributes to the martingale theory as well. But what I do here, I don't need to know that this guy is a martingale. I just leave it as there's a process defined this way. All I care about is that use the empirical process theory, and all I need is to show that the expected value of this guy is 0. Therefore, it can play a role of my usual residuals in an influence function. Okay. Any questions? So these two estimators should look pretty familiar. It's just an inverse probability weighted estimators. I want to be able, I use these two inverse probability weighted estimators to show identifiability and the identifiability assumptions that I need. And now, so that I can link the star guys to the actual mu that I use the P data distribution, the observed data distribution for. So let's just keep in mind that the phi of mu is the IPW kind of estimator for recurrent event processes, and phi of eta is the one for the survival, right? So there is nothing fancy here, really. It's just that you're dealing with two levels of coarsening, so you have to adjust it for two different weight functions. The first one handles the first layer of coarsening, which is a propensity score. The second one handles the second layer of coarsening, which is the censoring. Remember, this K is just that the probability of C being greater than X, meaning that the guy is not censored. Right? So I use these two to show that under the car assumptions that we made, this is the identifiable problem in general. So that's just useful in my causal world. To derive the efficient influence function, I use the von Mises expansion. All I need is to show that if this is my parameter of interest, under two different data distributions, let's call them, these are observed data distributions, they call them P bar and P. We don't need to be specific about them. If I identify this using P bar, P, the difference between these is going to be the expected value under P bar, expected value under P, times this function D plus some remainder terms. If I can show that, if I can come up with a D that satisfies this difference, then it gives me the von Mises expansion for my estimand under the different data distributions. And then later on, maybe the more familiar way of this is just you replace P bar by Pn, means that the empirical distribution average, this guy by P0. And this one become P1 Pn minus P0. This gives you the asymptotic linearity result, right? But von Mises expansion is really about the parameter. We want to see if the parameter can be linearized in this way. And in a nonparametric model, In a nonparametric model, there's only one gradient, and that gradient is give you the efficient influence function or canonical gradient. So if you just find one D that satisfies this, that would be your canonical gradient, which can use for efficient influence function. That's why it's helpful to do this, to go through this von Mises-Roth expansion. What we show is that if I define my D this way, this will satisfy the von Mises expansion with the R that includes the second order remainder terms. Second order remainder terms, meaning that there are terms that they depend on, for example, the residual between indicator of A minus pi times the indicator of the K process, for example. So this, again, if you look at this one, and if you know you've worked with causal effects, it's kind of familiar. It's not very weird. It's not off. So this guy, remember, this is the IPW estimator, right? There's a minus, so the minus sign, this is a minus sign, but it gets flipped because there's a minus coming out from here. So this is the influence, the tangent space generated by pi. This is the tangent space generated by the censoring process. And these are your nuisance tangent spaces. So you want to orthogonalize this guy, project them onto the nuisance tangent space, subtract it off. And this is projection of this guy onto nuisance tangent space generated by pi and subtract it off from pi, from the X and K, the failure censoring. This F guy is just defined as inference. This F is very similar to the kind of outcome regression in the usual average treatment effect. It's like an average treatment effect that you use like an outcome conditioning on A and L, right? But here your outcome just has this fancy form. Yeah. Yes. It is. Exactly. So this is the Gatto derivative in the direction. Yes. No, it's L2 norm. Yeah, L2P. So I use this exactly the way we use the efficient influence function to estimate. I'm interested in estimating this. So I set this guy equal to 0. That gives me my mu hat, the empirical average of this guy. One interpretation problem that I talked about, one way to deal with the interpretation issue is that to look at the increment. So basically, this I don't know, zeta function is the expected value of recurrent event given that you live beyond time t, right? If you remember, I talked about that this n star can be interrupted by failure. So this tries to handle that issue by conditioning on that you're going to be at risk. You're not going to fail before time t, and I'm counting the number of failure times after that. And and this one is going to be the probability of surviving beyond t. So it's just all I'm using is the conditional probability, rough conditional probability here I'm using. And I can, because I was using this landmark approach, it's just being each one is just the number of events that happen between time tj plus 1 here, times the probability that you live beyond tj. The main problem, this works perfectly fine if you're not interested in causality. The issue is that as soon as you become interested in causality, because you are conditioning on TA star greater than t, it becomes problematic. You want to condition on people that would have survived under either A, T0 greater than T and T1 greater than T. When you just condition on TA, you lose the interpretability for the causality. So this it's not ideal. It helps somehow, but it's not ideal to have the interpretable causal parameter. Schmidtly in 21, it's a very interesting paper. So the entire focus of that paper is to provide some estimand for this problem, the interrupted recurrent event processes. They don't provide any estimator. They just say these are estimands. one of the estimates that seemed appealing to us was this one, this ratio, where the expected value of TT is just is the expected restricted counterfactual survival. And the way they said we can interpret this ratio is that how many events I can expect relative to how long I can expect to live in the next 3 months. Right. So this way, they are not conditioning on any survival under certain potential treatment and potential survival time. And it has a kind of a nice interpretation. It's, if you look at the log of this, it becomes the difference between the two. It kind of looks like the kind of maybe the AT if you would like to have the contrast. And all the components here, another reason we picked this one is that, so we have the influence function for mu, we have the influence function for eta, and that's all we need to create influence function for these ratios using delta methods for influence functions. So we could use the theory we have for this estimand immediately without developing new theory. Any questions? No? All right. So let's go through some simulation. I have 3 baselines, and lambda E is my recurrent event intensity. Lambda D is for the failure time, death. And these are the betas are used, baselines coming from Weibel. This is my treatment model, so it's not a randomized. And censoring follows this hazard model as well. So the censoring depends on A and also depends on L. Yeah. Yeah.
This ratio.
Yeah.
Both the numerator and denominator reminds me of middle formula, which is something like, prevalence over, average, which becomes the incidence.
So is that
One lambda is the incidence rate, is the prevalence, and mu is the average lifetime. So when you look at it, it looks very much like.
I think so. I agree. The only thing is that I think in your example, you have the same process that you're taking expectation over. But this is a death process. This is recurrent event process. It's slightly different, I thought.
I know, but that gives, like the number of, on the average, the number of, cases divided by the average.
Right, right.
It talks about the incidence rate.
Okay.
Rate at which, these recurrences
happening. Exactly.
Comparing the
two group. Right.
I don't make the connection.
Yeah.
Very much like that.
No, sure.
It gives a good interpretation.
Yeah. So some quick simulation, really, we don't need the details that much. So I'm comparing it with the straight IPW estimators, which I showed you the beginning that I used for identifiability. This is the Xiaobo-Zhang estimator. It's very similar to the IPW estimator. The only difference is that there is no delta here. The delta embedded in the NU. So this one is more efficient, uses more data than these guys, because even delta is happening in future after times t. When it's 0, it's 0. It kills IPW. Whereas here, if the delta is not happening before time t, it still counts to create this ratio. So there's a lot of difference between the two. But the main issue with Xiaobo and Zhang, first of all, we have this, it's not efficient, it's an IPW. Another shortcoming of this is that they're assuming that the censoring survival is independent of L's. It means the censoring only depends on A. Right? So they use this because basically they simplify their life. We can use Nelson-Allen estimator, or even Kaplan-Meier. They could have used Kaplan-Meier NPMLE estimators for different groups. It's like to estimate the survival, censoring survival, right? So so this one So I consider different things for the propensity score model and the censoring model. In scenario one, both IPW and you are correctly specified, and the shall work are correctly specified because because the censoring does not depend on L1, L2, L3, right? So this is a scenario that we expect both of them work well. Scenario two, the propensity score is still correctly specified, so IPW could be reasonable, but censoring mechanism is misspecified because we have a bunch of L's there, and they do not allow for. And the third one, we specify the propensity score for IPW, and the censoring mechanism also cannot capture the assumption they need in the level. So both of them should break, and the one based on the two function that I showed you, the proposed one will still work. Here I showed the coverage probabilities, the coverage, the combination of coverages for all the scenarios. We see for scenario one, everything works pretty well. Slightly under coverage we have for IPW parametric model. For the age of parameter for age of one for some reason, but for age of two it does pretty well. For scenario two is when we expect the Schauble to break. We see that the Schauble is not working very well. So remember, this is the mean counting process. This is the survival process, so there are different estimates. And for the scenario three, when IPW and Schauble both we specify for this course, they work pretty bad. I think on the coverage quite significantly. Is the coverage for the 5% basically. Of the root and bias table of paper here, show that the bias is held with the root end and doesn't blow off, which is also kind of shows up here as well. But we expect it to behave well, just like we say coverage. I thought I had it here, but I think I had it in the application. But the professor in the method they do, the governor of estimator, we estimate all the parameters with super with non-parametric model. By norm or IPW estimator that are not governor, we cannot estimate the matrices towards non-parametric. So as soon as you start using IPW, I'm happy that it uses functions. You can even with talks, estimate the content between the question, and also know the right the corresponding English function because they have to take into account that they are estimated in the same thing. Anyway, so what I'm saying is that the variance for IPW and electronic variance is not overall. Recurrence of cardiovascular hospitalization, PM2.5, the terrible particle of the 2.5 micro mass, and they can be dangerous because keeping your lung and for cardiovascular, so result very system as well. There are a lot of studies that provide controversy effects and practices they project focus on the recurrence of CDD. They have their exposed for but here we want to have recurrence focusing on balance cells as they more in this data, people that in the state of Arizona, in the United States, dealing out in 1,000 substances. This gives me 200 7,000 or we consider the first 2 years that return to 65 and share the share that's to get the baseline value of health and average of the exposure and that to we have the exposure treatments. So what we did is look at the high exposure and we do that very on top of what's so high basically to zero. Here's the fact of the number of hospitalization in the subsequent 2 years. So there is sign and then we calculate 2 years after we look at them, I think like this is 69 days until the age of 60. Survival component, it's not a significant difference. Like it doesn't change the survival that much. Survival pretty much the same. Why the number of events the number of being exposed to the fiber of low start to deviate and the effect could become quite significant. So even in year 25, right, the year like you might see always just a 0.1 difference, like 0.6 minus 0.5. But with 0.1 number, when you scale it to the US population, it's about 130 to 160 billion dollars of cost, healthcare costs. Even this very small, like 0.1. So that's why, although in air pollution research, usually the effects is really pretty small, but when you scale it to the population level, this is pretty significant. The issue that I said is sometimes you see more or less recurrent events because it changes the survival probability. It's not challenging here, so even interpretation is pretty straightforward because both of them, they give pretty much the survival is the same in both groups. Right? It's just that we see that. So the only reason that you see that they deviate in terms of CVD hospitalization is because of the recurrent deaths. It has nothing to do with the death failure. But regardless, we also looked at this ratio to see if we get any different result. And going back to the interpretation, is that the expected number of hospitalization per unit time lived over the next 3 months. Here, you see that this becomes quite significant after 5 months of being exposed to a high level of exposure. And it's kind of a stabilizes. This effect kind of stabilizes, but as the the current event that I showed you is just that's it's just deviates more and more as we increase more. Yeah. Yes. Yes. Right. The ratio. And with a pointwise confidence interval, we get it if delta method for influence functions to get it for the estimand, the ratio estimator. Well, I guess that's it. Yeah. Thank you.
This notional discovery process.
Yeah.
Is there any, do you need to think about correlation in time, in your intensity, or you?
No, I guess that becomes more important if you want to study the gap time. But for the recurrent event, it's just a number. All you care about is the cumulative number. So that's fine. Yeah, no. Yeah. In front of myself, it's hard to talk about this kind of stuff. Thanks to myself. Exactly.
Ashkan again.
Thank you.